Welcome back to College Algebra. In this lecture video, we're going to begin to talk about another topic called the rational functions. So we mentioned rational function before. So for all those restrictions on the domain, now we're going to begin to give them a name. All right. So the first thing is called the vertical asymptote. So as you can recall, a rational function is a function that can be written as a quotient of two polynomial functions. Okay. So it's a fraction function, but your numerator and denominators are considered um, as polynomial functions, as polynomials. All right, where the denominator cannot equal to zero. If the denominator equals to zero, then the whole entire function will be undefined. So this thing called the vertical asymptote is simply referring to a vertical line where x equal to a number. Remember, vertical line x equal to a number, where the graph tended towards positive or negative infinity as the input approaches that vertical asymptote. Okay, so as your x value go approaching to that particular vertical asymptote, your function f of x can either your f of x or your y value. That's what it means. Your y value can actually be approaching positive infinity, or it can also approach to negative infinity. So I will demonstrate that when I graph it in the graphing calculator. Would that remind me to turn on my graphing calculator real quick? All right. So the steps on how to find vertical asymptote is very similar to is practically exactly the same step as how to find the restrictions on the domain. So the first thing we got to do is factor the rational function, factor the numerator and the denominator, reduce or cancel the common factors in the numerator and the denominator. So any common factor that were canceled out are the holes that we talked about before in the graph. So we got to keep that in mind when especially when we're stating the domain for our function. And set the remaining denominator equal to zero. Okay, whatever is not canceled, set them equal to zero. Then we can solve for the variable. So once we solve for the variable, then that x equal to a number will be our vertical asymptote. So real quick, let's take a look. So this problem, the denominator is already factored for me. The numerator is only one term, so I don't really have to do any factoring for this problem. Um, Reduce a common factor. So there's no common factor. This is one term on top, one term in the bottom. There's no common factors. So I'm just going to write down the word none. None. All right. We don't have to do any of them. Set the remaining denominator equal to zero. So let's do it right here. So I'm going to set whatever I do not cancel in a denominator equal to zero. So my x equal to 1. So remember now, we say set it not equal to 0, which is your restriction on the domain. So they are still the restriction on the domain. Now, officially, we call them the vertical asymptote. So here, I will see two vertical lines. I actually have two vertical lines in my graph. Some calculator will show the vertical asymptote, some calculator will not. Okay, so that's the reason why we went ahead and find our vertical asymptotes. Okay, before we actually do the graphing. All right, so this is actually our vertical asymptote. So let's graph it. Then we can answer this question as the x approaching to both vertical asymptote. Let's talk about what the y value will do. Then we can write out the domain. So I'm going to say 4x on top divided by open parenthesis for the entire denominator and open the parenthesis for my x minus 1. Close it for x minus 1 and open one for x minus 5. Close the x minus 5 and close the entire denominator. Let me go back to the standard window. All right, let me take a picture of this real quick. So here is my rational function, okay? So ahead of time, we know there is a vertical asymptote at x equal to 1. And so we don't quite see that. So you kind of know that there is a vertical line right here. Remember now, the vertical asymptote is the same as my restriction on the domain. So my function, my x value will never be defined at x equal to 1, because when x equal to 1, that will make my denominator equal to 0. So my whole entire function become undefined. So let me see, 1, 2, 3, 4, 5. There's one right here at x equal to 5. Okay. No, you know what? I'm not gonna make it thicker. So I'm just gonna write it right here. So I got a vertical asymptote at x equal to 1 and x equal to 5. All right. So from left to the right, as my function, okay, approaches to x equal to 1. All right. Once I cross over the x-axis, what is my y value doing as I'm approaches x equal to 1? My y value actually begin to go upward. So as x approaches to 1, the y value approaches positive infinity. That means my y value gets larger and larger and larger. All right. As my function from left to the right, as my x value approaches to 5 from left to the right. So I got two vertical asymptotes. So there's a piece of graph in between. So as my x value approaches, so when I pick up my x value from the right side of x equal to 1 and keep on going towards x equal to 5, my y value actually point downward. So my y value actually becomes negative infinity. As I'm approaching from left to the right, keep on going to negative infinity. My y value keep on going down. All right. So, so of course I still got another part right here on the right side of x equal to 5. You know, I'm actually approaching to infinity, which is not my vertical asymptote. So these two statements is referring to as x value approaching to your two vertical asymptote from left to the right. What's the y value doing? All right, let's write down our domain. So writing out the domain is the same as before. The two vertical asymptote are my restriction on the domain. So now we just call them specific names. So from left to the right, my x values is coming from negative infinity all the way approaches 1, but I can never equal to 1. That's why I'm using parenthesis. Union between the two vertical asymptote. Okay. My function does exist from 1 to 5, both using parentheses. So remember now, I'm using parentheses for the simple fact that the 1 and the 5 are vertical asymptote, so my function can never equal to it. So I cannot use brackets. So now the right side of x equal to 5. So this piece of function is actually from 5, keep on going to the right. Okay. So two vertical asymptotes, okay, or two restriction on the domains that divide my entire rational function into three pieces. That's why my domain has to also reflect, okay, to the three pieces that I'm looking at. Let's try another one. All right, let's factor. This problem is factorable. Not the numerator, though. The numerator is x plus 7. It's not factorable other than 1. So I'm going to go ahead and put it in the parenthesis over x squared minus 9 is the difference of squares. So that's x plus 7 times x minus 7. All right, step number 2, reduce the like common factor. So let's go ahead and reduce it. So my resulting function right now is actually 1 over x minus 7. But the function I'm going to graph in a little bit is the original one. Okay, original function or the one I factored before reducing. All right, so set the remaining denominator equal to 0 and solve for the variable. So my x is equal to 7. You got to write this down because that is your vertical asymptote. You got to say x equal to a number. Let me go back up here and write it. This is our vertical asymptote. You got to write. You cannot just say 1 and 5. You have to actually write x equal to 1, x equal to 5. All right, so let's graph it and see what the function is doing as the x value approaches the asymptotes. So I tell you what, I'm going to go back here and just put in x plus 7. So parenthesis x plus 7, close parenthesis, divided by 2 term in the denominator. I'm also going to put them in the parenthesis. So the part I'm canceling out is actually what? Will actually be the whole in my function. So even though I have 2 restrictions on my domain, the whole, which is x, cannot be what? I actually have a whole at x plus 7 equal to 0, so x cannot equal to negative 7. I have a whole at x equal to negative 7, okay, but I only have one vertical asymptote. So it appears that even though I only got one vertical asymptote, but I still have 2 restrictions on my domain, okay? So there's a difference between, that's why we classify, we class, when we talk about the restriction on domain, we got to be more specific. There are different types of restrictions, okay? I can have a hole in my function, or I can have a vertical asymptote. So x equal to 7. So they'll be somewhere right here. So my graph will never, ever touches x equal to 7. So my vertical asymptote is at x equal to 7. All right. So let's go and answer this statement. As your x value approaches the only vertical asymptote 7, what is your y value doing? So from left to the right, as my x approaches positive 7, my y value is actually what? Going downward, which is going to negative infinity. So what that means is, if I will plug in a number from left to the right that is so close to 7, maybe like 6.99999, a lot of 9, okay? Plug this number for the x. Then the y value comes out will be super, super, super negative, okay? Very negative. Now, what the other side of vertical asymptote is indicating, see how, so if I want to trace this piece, the other piece of graph, okay, I got to do it from up here and then keep on going to the right. So my y value on the right side of x equal to 7 is actually starting from positive infinity. My y value is actually from positive infinity, keep on approaches to the x-axis. So what I mean is, if I would put 7.00000, lots of 0 and a 1 into this, substitute that in for x, the y value comes out will be positive infinity, super large. Okay. Now, knowing I do have a hole in one vertical asymptote, so that means when x is equal to negative 7, 1, 2, 3, 4, 5, 6, 7, there's actually a little hole right there. Okay, so I'm going to indicate it with an open circle at x equal to 7. There you go. All right. So 2 restrictions on the domain, a hole and 1 vertical asymptote. So my domain got to be coming from negative infinity. My x value got to be coming from negative infinity, approaches 7. Okay, negative 7. Cannot equal to negative 7, union from negative 7, keep on approaching positive 7, but can never equal to it. So that's why I use a parenthesis. union. On the other side of the vertical asymptote, I'm picking my graph back up, picking my x value back up, and keep on going to the right. All right. So let me go to value real quick. Second count number 1, I'm going to demonstrate, put a 6.99999. Oh, it froze. You can try it. You can try at home. It can give you a very, very large y value. Oh, excuse me, a very negative y value. Graphing calculator just froze all of a sudden. It's all right. So that was the last question. So this video, we quickly talk about what a vertical asymptote is. Sometimes when student graph the vertical asymptote, it will show up on the graphing calculator. Sometimes it does not, okay? So that's why knowing how to find the vertical asymptote ahead of time and knowing how to find the hole in your rational function ahead of time does help us to find our domain. All right, that will conclude this video. Thank you for watching.